talk, which for those of you who know this stuff, you know that the fact that the existing adiabatic optimization algorithms are based on stochastic Hamiltonians is probably not the reason that we've found a lack of speed up, and I'll try to formalize some reasons for that in terminology that's maybe more familiar to computer science. But first I want to cover some of the history of this algorithm so we can understand the past, present, and future. So it starts with transverse field adiabatic optimization. So you want to minimize some cost function over the space of n-bit strings by preparing the ground state of some n-qubit Hamiltonian that's diagonal in the computational basis. And your scheme for doing this is to initialize the qubits in the ground state of a uniform transverse field and interpolate from this beginning Hamiltonian to the problem Hamiltonian. And the adiabatic theorem guarantees that if you do this running for some total time that scales polynomially in the number of qubits and the inverse minimum spectral gap along the adiabatic path, then this suffices to prepare the ground state of the problem Hamiltonian. Okay, so I call this transverse field adiabatic optimization because it's not the most general form of adiabatic optimization you could consider. For example, you could also insert an additional extra Hamiltonian in the middle of the adiabatic path. So maybe you have the same beginning and final Hamiltonian, but in the middle you turn on something else. And it was noticed that in the early days that for certain example cost functions, this non-trivial H extra can improve the gap, say from exponentially small to order 1. And then you also have this more general concept of adiabatic computation, which is a universal model. So if you do ground state adiabatic evolution with a local Hamiltonian, and you also allow yourself measurement and classical post-processing, as we usually do, this is a universal model. But it's worth pointing out that in universal adiabatic quantum computation, the final Hamiltonian is nothing like this diagonal cost function, but it's a Feynman-Kitaev circuit Hamiltonian. So sometimes people kind of blur the distinctions between these three, and that's why I'm setting the terminology. Okay, so what are some historical, heuristic reasons why people got so interested and excited about adiabatic optimization? So it's implementable as an analog algorithm. So there's hope that we could build a device that does this long before we could build a fault-tolerant circuit model quantum computer. And you know, there's a nice history where, so optimization principles, nature likes to do things optimally, or you know, physicists tend to think so, and this has inspired valuable classical optimization algorithms in the past. Another piece of intuition is that maybe quantum tunneling could allow for faster exploration of rugged energy landscapes in the classical cost function, and this intuition can actually be leveraged to obtain, like to build toy problems that exhibit this behavior where adiabatic optimization can be exponentially faster than classical simulated annealing, or indeed any local search algorithm. Just briefly to describe how those toy problems work, because I'll reference them a few times later. So to get this exponential speedup, you can use a bit symmetric cost function with a large energy barrier that creates a local minimum. And so you can think that your initial distribution, it's completely polarized, so it's centered around this n/2 Hamming weight. As you sort of turn down the transverse field, eventually you find this local minimum. And now if you're doing something like classical simulated annealing, it's got very low probability of ever stepping up onto this barrier. And because the barrier has some polynomial scaling width and height, it's got very low probability of ever stepping onto it and then ever crossing that plateau. And so these classical algorithms, you know, take 2 to the height of the barrier time to solve with local search. But the adiabatic algorithm, adiabatic optimization can, you know, if the barrier is not too tall or too wide, then can solve it in linear time.
What's the meaning of local search algorithm here?
So you do local search on the space of bit strings. So you're only allowed to change a constant number of bits in each search. That's the phrasing that's used in Ben's paper.
Okay, but I still don't understand, because like if we knew that this was the landscape, then we could make an algorithm that satisfied that condition and it would just go straight to 0.
You can spot it by inspection. Is that what you mean?
Yeah.
So you could imagine, for example, permuting the basis strings but keeping the cost function the same, right? And then you wouldn't know about this structure anymore.
Oh, really? So we actually proved the lower bound where you...
I would say so. This paper was in stock, yeah.
Okay, I'm just trying to understand the model. All right, maybe...
Okay.
Linear.
Okay, but the bad news is that we have no evidence of a speedup using adiabatic optimization over the best known classical optimization algorithms, certainly not with local Hamiltonians. There are a few results involving oracles, so you can obtain the Grover speedup using oracle Hamiltonians that kind of resemble the ones in adiabatic optimization. You can also obtain the glued tree speedup using a Hamiltonian oracle that represents the adjacency matrix of the glued trees. And this result actually involves a nearly degenerate ground space. So you have an exponentially small gap to the first excited state, and you end up mixing in the ground state and the first excited state. But then you have a polynomial separation to the rest of the spectrum. And then you have sort of intellectual descendants. The QAOA superficially resembles adiabatic optimization and briefly achieve the best approximation ratio guarantee for that problem. Even this year, you could see it as inspiring various rigorous algorithms. So the Google group has a paper about something that you could call reverse annealing. So this is you start in a classical basis state, you turn on the transverse field for a short time, and it lets you jump to another low energy solution. There's a very detailed analysis in that paper, and then there's also the algorithm we just heard about, which maybe kind of overlaps or takes some inspiration. Okay, but why is there no speedup? Why haven't we seen a speedup? Is it because the Hamiltonian is stochastic? Well, so even the empirical benchmarks, just to be clear, it's not just that we can't prove there's a speedup, because even the empirical benchmarks of using this algorithm as a heuristic do not indicate any evidence of a speedup over the best classical algorithms. Okay, and the most—
Not even the Grover speedup?
Well, that's an oracle problem, but that's proven.
But for the Grover speedup, you need a non-local Hamiltonian.
Yeah.
And so if you have local Hamiltonians, we don't know of any speedup.
Yeah, wow.
No, I think you can get the Grover speed up without using the projector. Oh, you mean because the oracle piece is a projector?
Yeah.
Okay, that's true.
Okay, and the most commonly cited reason for this lack of speedup is that transverse field adiabatic optimization is stochastic in the computational basis. So what does that mean? A Hamiltonian is called stochastic if in some choice of local basis, all of the local terms have matrix entries that are 0 or negative. Okay, and this word, it's not just my enunciation, it's a combination of quantum and stochastic. So, and physicists have known about these Hamiltonians or recognized them for 40 years or more, and they say they don't have a sign problem. This implies that the equilibrium states are on the border of quantum and classical physics. So an example of these stochastic Hamiltonians, really the example, so these transverse Ising models, so they're stochastic now in the Z basis, right? Here are the matrix form of these Pauli operators. So you can see that all the off-diagonal elements are explicitly 0 or negative. And in fact, it doesn't matter what's along the diagonal of this Hamiltonian, so we can also consider generalized transverse Ising models with disordered interactions. And in fact, these generalized transverse Ising models are universal for simulating stochastic Hamiltonians and for stochastic adiabatic computation. This is one of these proofs that uses perturbative gadgets, so you pay a pretty expensive polynomial overhead. But as far as, maybe as theorists, we can just focus on this class of generalized transverse Ising models as capturing the entire class of stochastic Hamiltonians. Okay, so what about this property about the amplitudes in equilibrium? So if the Hamiltonian has real and non-positive matrix entries, then minus beta h, where beta is some positive inverse temperature, is a non-negative matrix entries. So if you expand this guy as a series, right, you're just adding up every term in this series is a non-negative matrix. You're adding them together, therefore this e to the minus beta h is a non-negative matrix. And so
even the diagonal entries, right?
yeah, that's right. Yeah. Okay. Yeah. So you can always add an identity. So yeah. Okay. Now, as you take the limit to very low temperature, right? The e to the minus beta h. Well, this is written unnormalized, but it becomes the projector onto the say you have a unique ground state. It becomes the projector. Therefore, you can just see from this simple calculation that there's a choice of global phase that gives the ground state non-negative amplitudes. And in fact, if the Hamiltonian is an irreducible matrix in the basis you're considering, then all of the ground state amplitudes are strictly positive. And so if your transverse fields are non-zero, then you have an irreducible matrix, and so none of the ground state amplitudes are 0. Okay, and so further delving into the special properties of these stochastic Hamiltonians, it really has to do with their path integrals. Don't mind the term Euclidean, it's for physics reference. So we can expand the partition function as a path integral, right? A sum over paths of some product of amplitudes, very similar to the sum over paths that we heard about in Scott's talk. But in this case, because this e to the minus beta h over L is just some integer, the length of your path, because that's a non-negative matrix, every path contributes a positive weight to this sum, which is very special. So you can define a probability distribution on the space of paths. And for sufficiently large inverse temperature, this probability distribution has the ground state probability distribution as a marginal on any sort of given time slice in the path, right? So if you trace everything out, then you just get either the thermal probability distribution or even the ground state probability distribution. Okay, so now having described that, I can tell you about the quantum Monte Carlo algorithm. And the idea is just that you're going to do Markov chain Monte Carlo for stochastic path integrals. So because the ground state of the Hamiltonian becomes a marginal of a Gibbs distribution on a larger state space, you just rewrite all these path terms as some effective energy function. Then, really, as long as you can efficiently sample from the distribution, then the path integral will be a faithful approximation. You're not discarding entanglement or anything like that. Okay, and this quantum Monte Carlo works very well in practice, but the convergence of the Markov chain is hard to theoretically analyze, and so we don't understand why it works as well as it does. Okay, now I have to talk about D-Wave, the elephant in the room. So D-Wave implements a noisy version of transverse field adiabatic optimization that they call quantum annealing. The single qubit coherence times are on the order of nanoseconds. The annealing times are on the order of microseconds. Yes?
Could you be a little bit more specific about what you mean by we don't understand the MCMC? Do you mean the limit when L goes to infinity?
We don't know the mixing time of the Markov chain for this distribution.
Or fixed L?
Fixed L. So L, think of L as polynomial in N. So yeah, you have these facts about the single qubit coherence times being much less than the total annealing times. You can draw your own conclusions. There's also substantial open system effects and calibration errors in the device, and yet it successfully solves 2,000-bit optimization instances. So in my opinion, it works better than theory might predict, and maybe in some sense confirms these ideas of inherent robustness. Okay, and so just to tell you about the current status as I know it, so for instances designed to give D-Wave every advantage over its classical competitors, it's able to match the performance of the best implementations of the best classical algorithms on a modern single-core CPU. So that's not something that is completely easy to do, and in fact, the classical simulations have improved by orders of magnitude in just the last 5 years in order to stay competitive, but that's how I would describe the current status. Yeah.
Would you give instances of this?
So they're specifically, for example, designed to frustrate this HFS algorithm, the Hans-Frieda-Selby algorithm that takes advantage of the chimera structure of the D-Wave graph. So they're pretty complicated. They're pretty contrived.
Okay, so there were the 1,000 bit implementations which were actually designed as as these instances for the unit cell and then distributed in some ways. Are those the ones you're referring to?
Yeah, the frustrated loops is the term used for them. Yeah. Okay, yeah, they involve planting a solution that's designed to foil some of the stronger classical competitors to D-Wave. Okay.
But the planting is also such that the D-Wave machine will find it?
Yeah, I mean, the point is that it has trouble. They both take a few seconds to find the answer for 2,000 bits. That's kind of the current.
Okay, so maybe we should talk about this afterwards, but this model that we had, the SSSP model, I think we worked with it, and we could at least do the 1,000-bit
yes.
versions of those.
So wasn't that actually the 2013 quantum annealing without? So you did later. Yes. So people still use spin vector. So now that algorithm with minor improvements is called spin vector Monte Carlo. And indeed, people still use it. And if you just throw a random instance, right, it's likely to be easy, and a lot of these methods, including the SVMC, will beat D-Wave. Yeah. So it's only when you choose instances that really foil that simulation and all the others at the same time.
But a couple of years ago, we went through these particular instances,
Yeah.
and we were able to simulate them as well.
Oh, these.
Yeah.
So maybe it's not that it does better. It's just
Yeah, I'm not saying it does better.
No, but we could do it classically with this very simple local model and do it as well. As the,
that's what it says, as well. It doesn't say that D-Wave is better.
No, but these are not the best algorithms. This is just a very simple local algorithm with 1,000, just 1,000. So it's not really the best algorithm. It's something very, very basic, right? So that's the point.
So I'm trying to give the best case scenario, but you're right that many times even this very simple algorithm, yes, is vastly superior to the D-Wave performance. Yeah. Okay, I just want to also share this slide about empirical benchmarks that are actually based on instances that are really built from that spike problem I told you about earlier. So they're designed to foil algorithms like classical simulated annealing. And the Google group put out this paper in late 2015. So you can observe a few things, which, so first of all, the first thing I notice is that the D-Wave scaling curve looks very similar to the quantum Monte Carlo scaling curve. But they also pointed out that there's this 10 to the 8th factor, prefactor of speed up, but also you're not comparing against the best possible classical algorithms for this particular set of problems. But what I actually just mainly wanted to point out about this slide is that even when they're saying that D-Wave is doing well and it's beating classical algorithms, that the actual scaling curve seems very similar to quantum Monte Carlo. So I want to reinforce this idea that, we see quantum Monte Carlo matching the performance of the D-Wave, and that is deserving of even further explanation. We don't understand the mixing time of this quantum Monte Carlo Markov chain, but for some reason these scaling curves tend to match. Okay, so we have the stochastic simulation conjecture, right? This is one of the old grand conjectures in Hamiltonian complexity, that stochastic adiabatic computation can be classically simulated in some time scaling polynomially the number of bits and the inverse spectral gap, simulated in the sense of sampling the ground state probability distribution in the computational basis. And okay, so in order to make this conjecture sensible, it's crucial that the gap refer to the minimum gap, because you could, for example, take an NP-hard instance, or you could take some ensemble of NP-hard problems with a unique ground state, and then when you perturb them by a tiny transverse field, you'll retain a constant gap. So it's crucial that you don't refer to the instantaneous gap of the Hamiltonian, but the smallest gap that occurs along the path in order to get a sensible conjecture. And this is actually quite difficult because Markov chains are designed to forget where they came from. And so making essential use of the adiabatic path in your simulation attempt is quite difficult. And there's kind of like a conventional wisdom for people who have thought about this problem that it's really about the use of warm starts, that is, avoiding doubly exponentially small amplitudes in the quantum ground state. I can actually show that this doesn't happen. So the ground state amplitudes are never smaller than this in the relevant parameter regimes for these generalized transverse Ising models. And so, if you think of the mixing time of a Markov chain, right, it depends logarithmically on the reciprocal of the minimum probability of your stationary distribution. But because that's never doubly exponentially small, these warm starts are actually not the answer. You need to make even more essential use of the adiabatic path. Okay, so reviewing some results on the stochastic simulation conjecture. Yeah.
How can it be that the ground state has super exponentially small overlap with all states? Because isn't that a basis? All x and 0, 1 to the n, isn't that a basis for all states?
Yeah, it is. It is. So the fear is that you have some states, some computational basis states with doubly exponentially small amplitude.
Oh my God.
Less than that.
Yeah.
Sorry, I thought you were saying otherwise.
Okay, great.
Yeah, I got you.
Okay. All right, so the most general sounding result to date on the stochastic simulation conjecture is the polynomial time simulation of frustration-free stochastic adiabatic optimization. And it's a great result, but I say it's general sounding because frustration-free sounds like a very general class, but it doesn't include this class of frustrated transverse Ising models. So it doesn't attack the stochastic adiabatic optimization in a sense. And all the other rigorous progress that we have are on cases that we know are easy for some reason. So for example, ferromagnetic models on any graph and essentially any temperature, and also the spike Hamiltonians I told you about, and 1D models up to modest inverse temperatures. And actually, even out of all of these, it's only the result about spike Hamiltonians that does use the adiabatic path in a crucial way. The others, because there's sort of no computational complexity in the 1D models or in the ferromagnetic models, you can just kind of jump to any setting of the parameters and just run the quantum Monte Carlo at that setting. And then finally, all the existing quantum, so it's not just a matter that we have a candidate simulation algorithm and we don't know how to prove it works. Because thanks to Matt, we know that all existing quantum Monte Carlo algorithms are inadequate for the most general form of the conjecture. Because you always encounter, there are these two types of obstructions, and all the variants of quantum Monte Carlo will be foiled by either these topological obstructions, which have to do with the winding of this extra path in the path integral, or they have to do with differences between the amplitude and L2, amplitude distribution and probability distribution. Okay, so now I want to tell you about something that is actually quite simple, but maybe surprises some people. So I'm going to tell you about quantum supremacy with stochastic ground states. Okay, so stochastic adiabatic computation can't be universal unless the pH collapses, because approximating stochastic path integrals is in post-BPP. Okay, fine. But Bravi et al. Define H to be stochastic if there is any choice of local basis in which the condition on the matrix entries of H is satisfied. And so it's possible that you could have a theoretical quantum supremacy result by sampling a stochastic Hamiltonian in a rotated basis. And in fact, we all thought about this just a few days ago. The output of an IQP circuit is the ground state of a local Hamiltonian, where you've just applied local rotations to a very simple gap stochastic Hamiltonian. Okay, so this Hamiltonian, UHU dagger, is stochastic. But because it's the output of an IQP circuit, sampling it gives you theoretical quantum supremacy. And in fact, you can get even stronger results of this nature. One local rotation suffices to make the 2D cluster state Hamiltonian used in MBQC explicitly stochastic. So this is it's a bipartite lattice. You color the vertices red and blue, and you apply Hadamard, say, to all the red vertices, and it decomposes your stabilizer Hamiltonian into terms that look like this. There's actually a minus sign in front of these. And this actually has now recently appeared in a paper by Kisuki Fujii with the title Quantum Speedup in Stochastic Adiabatic Quantum Computation. Really, he doesn't do the cluster state, he does the union jack state, and there's more to it, but that's really what it is. You're not getting the speedup from the adiabatic part of the computation, you're preparing one of these resource states, and we know that sampling those gives you quantum supremacy. So finally, how can we evaluate this non-stochastic quantum adiabatic optimization? So I'm actually just going to formalize the thing that Matt was telling us about localization. I'm going to formalize it in terms of the concept of conductance that we're familiar with from Markov chains. And it also is something we could call an isoparametric inequality. So we're going to relate the ground state geometry to the spectral gap. And basically, it's about generalizing a known result for Markov chains and stochastic Hamiltonians to the non-stochastic case. Okay, and it furthers our understanding of the probability distributions that can arise from these gap non-stochastic ground states. That's the reference. And so we're going to think of the labels of the basis as vertices of a graph, and we'll think of the ground state as a probability distribution on that graph, exactly like the picture of the hypercube. Okay. And then we're going to connect two vertices to form this graph by an unweighted edge if the corresponding Hamiltonian matrix entry is non-zero. And then I want to define the interior boundary of a set of these vertices as those vertices inside the set that are connected to something outside of the set. Okay? So here, just a bit more notation. We'll make the Hamiltonian positive semi-definite. This is the operator norm. This is the spectral gap. It's just the bare spectral gap above the ground state. And so now, if you take any arbitrary choice of basis and consider the ground state probability distribution in that basis, and any subset with less than half the total probability, then you can essentially use this to form a small weight cut, a variational state that tells you that the spectral gap has to be that small, okay? And the point of this, all right, the power of this is in the last two points here. So it depends on the range of the k local terms in the Hamiltonian, because those affect sort of what we define to be the interior boundary, but not on the details of the Hamiltonian couplings, not on whether there's a sign problem or not. And so for a given probability distribution, this inequality constrains the spectral gap of any local Hamiltonian having it as its ground state in any choice of local basis. And so if you just take any probability distribution that a Markov chain will struggle on because it has a set with small conductance, then having a non-stochastic Hamiltonian is not going to help you to satisfy, to sample those types of distributions using at least adiabatic computation. So kind of concluding, so simulated quantum annealing we observe works really well for stochastic adiabatic optimization. And so people say that this non-stochastic Hamiltonians are necessary for quantum speedup. Well, necessary maybe, but not sufficient. But so sampling a stochastic Hamiltonian in a locally rotated basis can yield theoretical and practical quantum supremacy. Practical here meaning that quantum Monte Carlo gives you samples from the ground state probability distribution in the basis in which the Hamiltonian is stochastic, and you can also use quantum Monte Carlo to compute local observables in any basis, but you can't get samples from a rotated distribution using that method.
Theoretical supremacy means you can like sample distributions that if you do it classically, then pH collapse.
Yeah, that was a couple slides.
So there's a certain, if you take like this IQP model, as you say, so you start, that's like the ground state of the Hamiltonian is just some very simple, like I guess X is the Hamiltonian, right, or something like that, and then you have a locally rotated basis.
Yeah.
And so sampling from that gives you a certain power. If you can sample from a locally rotated, more general stochastic Hamiltonian, like locally rotated transverse-siding model, is that the same power as sampling from that one, or is that a bigger power?
I think it depends on how big of the local rotations you use exactly, right? Because you have to decompose the k-local interactions into that transverse-icing form, and when you use these perturbative gadgets. But you're saying, is it possible it gives you an even greater power? Well, it couldn't be greater, yeah.
Well, I mean, yeah, this is what I'm asking. Like, so a simple instance of one of these Hamiltonians would be one that's just the transverse field or just a z-term or something like that.
Right.
And so already sampling that rotated gives you a certain computation of power. So if you look at a more general Hamiltonian that has both the z-term and the transverse field, or just a completely general one, this full complexity class of, I don't remember what the symbol is for all these stochastic Hamiltonians. If you can sample that one rotated, could that be a bigger class or some other guarantee that you get because now you can rotate a more general family?
It's a little hard to think about, right? Because you take what you have and you augment it with post-selection, and the point is that already after rotating these one local guys and you augment them with post-selection, then they become post-BQP, right? So yeah, you can't be much more than that. Okay, right, so again, one of the messages here is that adiabatic computation with non-stochastic Hamiltonians is universal, but this doesn't mean that the non-stochastic Hamiltonians will improve the performance of adiabatic optimization. We just don't know, and there are some reasons to see inevitable limitations. That is, some explicit probability distributions inevitably take a long time to precisely sample using purely adiabatic evolution. And part of the lesson here, and Daniel made this point earlier in the beginning of Matt's talk, is that maybe the spectral gap condition is too pessimistic. It's okay if you go into the excited state if you just have a few low-lying solutions. Just more generally, it would be really nice to have more general theoretical conditions to capture the success of these kind of algorithms that go beyond the sufficient condition of having a large spectral gap, because it's so easy to show that those spectral gaps become small, these bare many-body spectral gaps, so that if we had a more robust condition for why the algorithm works or not, that would be great. And then also, I think the lesson from universal adiabatic computation is that measurements and ancillas are very powerful. That's it. Thanks.
Further questions?
I have a question maybe jointly. So, with this stochastic condition, so is there a way that one can interpret Matthew talk as saying, well, stochastic Hamiltonians, and could one say, interpret the algorithm right in terms of just instead of phase estimation, working adiabatically, but not with the exact path that you were talking about, and then saying, well, maybe it's more powerful than one thought.
Maybe what?
Maybe it's more stochastic.
Well, I think one answer I would say is that it actually could be good to have this class of Hamiltonians because it at least guarantees some kind of constructive interference. Now, I don't think, for the kind of speed up I was talking about, you wouldn't want to actually run the adiabatic by a slow changing because you're talking about a small overlap with the states, you would need to run for a very long time. So you want to do it more subtly, but I think it says that it could be good. It gives some constructive interference.
So I guess the question was, well, in view of that, would you, with the conjecture, would you still believe this conjecture that?
So we expect at least a quadratic slowdown in the spectral gap because this Grover problem, right? These oracle Hamiltonians can also be translated into the quantum Monte Carlo context. And actually, even a stronger observation is this glued trees problem, which is that, so even though you leave the ground state, and it's commonly said to be non-stochastic because you leave the ground state, right? But we also said the thermal density matrix has this special non-negative matrix entry property. So if you're at sufficiently low temperature, you have just overlap with the ground state in the first excited state. So it does appear that at non-zero temperatures, right, you can do something with stochastic quantum annealing, let's say, that you couldn't simulate with quantum Monte Carlo, at least in an oracle model. There is some sense in which we might want to scale back the stochastic simulation conjecture a little bit. Like these obstruction examples make essential use, in my opinion, of non-constant degree gadgets to translate them into Ising models. We don't know that there are counterexamples to rapidly mixing Pythagorean Monte Carlo in the case where you have bounded degree interactions, for example. So maybe the conjecture should be made a little weaker.
And just to follow up with the non-stochastic, you were talking about you should just look at the interaction graph, which is correct. But then, could you say the complexity really goes into the fact that with non-stochastic it's an irreversible walk, and so or it's reversible but weighted in some way, and so now the stationary distribution is going to be very different, and you can get to highly non-uniform stationary distributions very easily.
Well, and that was kind of the point of the conductance argument, is that you can't avoid, that bound was for the fully non-stochastic case, so that, okay, maybe one thing I could say.
Isn't it the weighted conductance where these weights on edges are?
No, it's just vertex expansion. That was the point. Yeah, it doesn't depend on the details of the Hamiltonian couplings. It's just the probability on the boundary over the probability in the interior.
On the boundary, isn't it weighted now by the stationary distribution?
Yes. So
it's not the vertex expansion anymore because it's now weighted by.
Oh yes, it is weighted by positive weights though.
Right. But
Yeah.
those weights can vary exponentially now. So certain vertices become exponentially suppressed.
Yes, that can be true. So actually, I didn't go into it, but if you wrote out the full conductance form where you count across the edges, you see that the edges with the wrong sign actually make the upper bound smaller. Right. But I will grant your point, and I agree that if anything, the power of non-stochastic adiabatic computation has to be not in how it arrives at the distribution, because it's foiled by the same kind of distributions as Markov chains are, but just in the fact that we can't classically understand or classically access that distribution. So the power would have to be in the distribution rather than the dynamics.
Can I ask a question about that weighting there, just to follow up? So yeah, you said that, so maybe I misunderstood something. It seems like there's two weights. One weight is that there's the weight of the wave function, so that if the wave function has very small probability somewhere, it doesn't matter so much. But also, are you saying that one good thing about having all terms in the Hamiltonian with the same sign is that you don't get some canceling of this, and so it can
Absolutely.
be easy to get, oh, I see, okay.
Absolutely.
Terms may end up canceling.
Yeah.
can I ask one more question?
Yeah.
So, back to this sampling on a rotated basis.
Yeah.
It seems like many states that are ground state, many Hamiltonians, we think the ground state can be approximated by something that's a local quantum circuit applied to just a product state.
Right.
Just approximately, we don't have to prove it in many cases, yes, in many cases. So, do you think there could be some extra power? You know, you can, with these Hamiltonians, you can build some topologically ordered states which can't be written in that way. You know, that's a state where, you know, if the state is not topologically ordered, there's sort of no need if we allow local rotations to set it up as a Hamiltonian ground state. If it's topologically ordered, then maybe sampling by a local rotation of that may give you some extra ability.
Okay, that's interesting. So in those topological cases, if you have a degenerate ground state as well, already in the stochastic case, right, your additional ground states will have some negative phases as well.
Yeah.
So yeah, could that give you some additional power? I'm kind of back to the post-BQP thing when you augment it with post-selection, but maybe I just didn't understand.
Okay, let's thank Elizabeth.